So now let us see the Rayleigh's criteria of resolution. So here we are going to learn the resolving power of microscope, telescope and optical instruments. So for incoherent sources, this is for incoherent sources. So if we are using incoherent sources of light, we are observing suppose stars through a telescope. So the light emitted from stars are incoherent. So the Rayleigh's criteria of resolution gives better result for incoherent sources. There are other criteria, Sparrow criteria, all others, which give better result for coherent sources, but for incoherent sources we use Rayleigh's criteria of resolution. So first of all, we should see what we mean by resolution. Now suppose I draw some points, I will draw some points, and so when our camera is focused on this area, then you will see the 2 points to be a single point, but when the camera is focused on a small area, you can resolve the 2 points. This is what is resolution. Suppose I draw a point here and I am drawing another point very close to it. Now these 2 points, so when the camera is zooming only on this part, the camera is able to resolve these 2 points. You can see that these 2 points are really 2 points. But when my camera is focused on this part, that is our main camera, then in the main camera these 2 points appears as a single point. This is what is called resolving power. The main camera, which is focusing this whole area, cannot distinguish these 2 points. In that camera, the 2 points cannot be resolved. But in the actual my zoom camera, the camera which is focused within this region, these 2 points appear as different points. That camera lens is able to distinguish these 2 points. This is what we call as resolving power. So now let us see that how the diffraction, camera is also an instrument, how it can resolve 2 different objects. So suppose this width, and here there are 2 objects, S1 and here S2. These 2 objects are there, and this is a slit, circular opening. My camera lens, it also has a circular opening. The light coming from the camera lens, just the camera lens acts as a slit. In telescope, the objective acts as a slit. In microscope also the objective acts as a circular opening. So that acts as a diffraction, Fraunhofer diffraction slit. Now you see the image, you see this is the screen and this is the image, geometrical image of S1 and S2 formed. Now these S1 and S2 are point objects. So due to this S1 on this screen, we will have a airy pattern. So the image will be in the form of discs. The image will be in the form of discs. Now due to this S2, the airy pattern interference will be like this, and so here you will get discs. So what happens? So on this you just see there are 2 places here. This place you have discs and here also discs. These are airy patterns. So this point object will not form a point image, it will form discs, the airy pattern. So what happens when we see through this S1 and S2, their diffraction patterns overlap and they get mixes. So the Rayleigh criteria tells us that how much, to what maximum extent, if their diffraction pattern overlaps, then we can distinguish. Now suppose I am seeing these 2 points, so now this is my eye, a small opening, here there will be a small opening, and so light from different S1 and S2 comes here. So what happens, on the retina the discs will be formed. So when we see a point object on the retina, its image is not formed, but the diffraction pattern is formed. To what extent they overlap will decide whether we will be able to distinguish S1 and S2 as 2 points or a single point. So now you can take a example in our daily life. Suppose we watch some movie in a LED TV. So now when we watch from large distance, we can view the images, but when we are very close to the screen, then we find that there are pixels, dots. So when and at that time the image does not appear. So what happens at that distance, at a very close distance, our eye is able to resolve the individual pixels. That is a term we say, it pixelates. So when we are so close that we can resolve each pixels, then we can't get an impression of an image. So when we are far away, when our eye cannot resolve the individual pixels, then the whole image appears. This is what resolution is. So now let us see what is the Rayleigh's criteria to distinguish 2 points by a diffracting system. Now suppose this is my slit, so I have to create a small opening. So this is wide enough, and here I have placed 2 S1 and S2. So one is, so here we have this screen. Now according to Rayleigh criteria, suppose this is the intensity profile, the airy pattern of S1. So this is S1 dash, and what about S2? It is again something like this. So now what we observe? We observe that when the first airy pattern forms on the central maxima of the other, then we are able to just resolve the two objects. So we will get an impression that, you see, we can't actually draw with this marker. So when so something like this structure type, something like this will be formed. So on the screen, the two, if they are well resolved, then you will get some discs. These are well resolved objects. But when they overlap, so when they are just resolved or critically resolved, they appear to be like this. So according to Rayleigh's criteria, according to Rayleigh's criteria, the two objects are just resolved or critically resolved if the first minima of one airy pattern falls on the central maxima of the other. That means we have already seen that the angular position of this for circular aperture, here circular opening is given as sin theta is equal to 1.22 lambda by A, where A is the diameter of this opening. A is the diameter of this. So you see this is the central maxima and this is minima. For this also there is central maxima, this is minima. So this whole angle theta or phi, let us call it, this phi is equal to sin inverse 1.22 lambda by A. So this diffracting aperture has a resolving power of phi equal to sin inverse 22 lambda by A. That means two objects which subtends an angle phi equal to sin inverse 22 lambda by A are just resolved by this instrument. So if a camera lens has an opening of this much, then this is the diameter of the lens, any telescope or any optical device. So how much will be the resolving power will be simply proportional to the diameter. More will be this A, smaller with the angle. So finer things, that means we can resolve two closely spaced objects. So more will be the diameter of the lens, better will be the resolving power and better will be the image quality of the camera. Now let us see that when two objects are critically resolved, unresolved and well resolved, how will be the interference, that is the diffraction patterns. So you see this is the Airy pattern, the diffraction pattern of one object, and this is suppose another object. So you see we will find that these two images, this is the diffraction pattern of one image, another image. So they are well resolved. So this is well resolved. Well resolved. If they are point objects, then we will find the image something like this. So two objects, clearly we can see that we can recognize that there are two objects. This is well resolved. Critically resolved. So this is the diffraction pattern of the first point source. This is the central maxima, and when central maxima of this coincides with this minima and its maxima with this minima, so they are just resolved. So when they are just resolved, this is the shape. So here we will get a picture like an 8. So they are just resolved, we can just say that there are two objects. Now when they completely overlap like this, you see this is unresolved. So the image will be, we can't. Now let us see resolving power of a telescope. Now in telescope there are two lenses, objective lens and an eyepiece lens. The main lens is the objective. So what happens? The objective lens produces a image of distant objects, and this image has suffers from diffraction effects, and eyepiece simply magnifies the image found by this. So, we can say that on the eyepiece or on our eye, the image is not formed, but the diffraction pattern of distant objects is formed. The objective lens serves as the opening, the slit of for. So, now let us see that this is the, suppose, objective lens. This is the objective lens, and there are two distant stars, one star is S1 and one star is S2. So, this is S1 and this is the, so here this is the screen means here our eyes may be placed or the eyepiece is placed. So, you see, with our naked eye also we can see stars, but when we see sky we always find there are stars, we cannot find galaxies and all those things. But suppose we see a star, and when the same star we see through a galaxy, we find that that is not a star, that is not a point source. In that point source there are large number of other point source, that means that's a galaxy which contains again say millions and millions of stars. So, with the help of a large telescope, this time I am able to resolve the individual stars, but with unaided eye, but with naked eye we just see a light source and we get an illusion that this is only a star. That means our telescopes can resolve better than our eye. So, now suppose S1 and S2 are two stars which we are looking from this objective telescope, this telescope. So, what happens here, according to Rayleigh criteria, we will have the minima of one diffraction pattern coinciding with the central maxima. So, this angle will be given by phi is equal to sine inverse 1.22 lambda by A. Now, the resolving power of a telescope depends on the diameter of the objective lens. How? You see, the minimum angle at which the two stars or distant objects that can be just resolved is given by Rayleigh's criteria by phi is equal to sine inverse 1.22 lambda by A, where A is the diameter of the objective lens. So, this phi, you see here, this phi depends on sine inverse 22 lambda by A. Now, this angle is so small, so we want my telescope to resolve two objects, two stars at a very small angle. So, what we do is we have to, in order to minimize phi, we have to increase A. More is the diameter, better will be the resolving power. Next, what we can do, if we decrease lambda, then also we can increase the resolving power. Lesser the lambda, better, or we can see smaller angles between two stars, means two stars which are separated by a small angle, that also can be resolved if we decrease lambda. For example, when we use optical light, optical telescope, then the wavelength of light is in visible light, that is nearly 7000 angstrom for red and 4000 angstrom for blue light or violet light. So we have a limitation. Now suppose I use X-rays. X-rays have a 0.1 angstrom to 100 angstrom. This is the wavelength range of X-rays. Suppose I use 0.1 or suppose 1 angstrom also. So 1 angstrom means nearly it is 4000, 5000 times lesser. So we can resolve 4000 and 5000 better if we use X-ray telescope. But you see, we can't see through X-rays. So in place of eye, or in place of here, we have to use some detectors, electronic detectors. Now if I use gamma telescopes, there again further we can reduce this wavelength, and so the resolving power of X-ray telescope, gamma telescopes are very large, thousand times larger than optical telescope. But we can't use this X-ray telescope and gamma telescope from the surface of earth, so we have to keep this telescope out of the atmospheric interference. So we have to keep this telescope in space. That are some examples are Chandra telescope, Hubble telescope. These are X-ray telescopes which has been permanently stationed in space away from atmospheric interference, and so they gave more resolving power than optical telescope. Now we will see the resolving power of a microscope. Now let us see resolving power of a microscope. In microscope, we had this objective and we place objects between focus and pole, but very near to this focus. So let us see that there are two objects. Suppose this is the focal distance, nearly focal distance, but this is not the focus. Focus will be exactly here, somewhat away from here. So let us see that here I have two objects A and B. Through a microscope, we see two points A and B, two objects, two virus, two bacteria, anything you say, microorganism at A and B, and this is B dash and this is A dash. So suppose this is Y and this is Y dash. What is A and B? Through this microscope, A and B are the closest points which can be seen as two different points, A and B. So this is the minimum distance that can be resolved. Y is the minimum distance that can be resolved with the microscope. Now this image is formed, B is a point object, here its image is formed according to ray optics, and A image, the image of A is at A dash. But since these are point objects and according to diffraction, here the image will be in the form of discs and here image will be in the form of discs. As a result, they will overlap and they can be resolved according to Rayleigh's criteria. Now this angle is phi according to Rayleigh's criteria. According to Rayleigh's criteria, the points A and B are just resolved, A dash and B dash are just resolved if phi is equal to 1.22 lambda by A. So, we can write this is sine inverse, since these angles are so small that sine of theta is theta. So, simply phi is 1.22 lambda by A, where A is the diameter of this lens. This is according to Rayleigh's criteria. Now, we can further let us write it as phi is equal to 1.22 lambda by A, that is sin phi or tan phi, that is equal to y dash by, suppose this is V, y dash by V. So, this is 0.1. Now, from similar triangles, this is phi and this is also phi. From similar triangles, we say y dash by V, y dash by V is y by this distance is nearly f. Actually, this distance is smaller than f, focus is somewhat here, but very close to f. So, I can assume this as f. This is second point, and so we can substitute it here. So, we get from 1 and 2, from 1 and 2 we get 1.22 lambda by A is equal to y dash by V is y by f, implies y is equal to 1.22, y is 1.22 f lambda by A. What is y? Y is L min, the minimum distance that can be resolved by a microscope. If two objects, two microorganisms are separated by L min equal to 1.22 f lambda by A, then we can see through this microscope two microorganisms. But if that distance is lesser than this, then we can't see two objects. We may think that this is only one microorganism, and if it is more than this, then we can see it is as two. So, this is what is microscope is able to resolve this minimum distance. Now, the resolving power of a microscope is defined as the reciprocal of the minimum distance which can be resolved. So, if I denote R as the resolving power, then R is L min, that is A by 1.22 f lambda. This is the resolving power. Now, you see, this is our lens, objective lens. This has a very short focal length. What is A here? Here to here distance is A by 2. The total diameter is A. So, this is A by 2, this F. Now, we see the paraxial images. So, this angle is, suppose I call this angle as theta, then we can say tan theta as A by 2f, or tan theta can be further written as sin theta also. So, R will be equal to, now f by A, that is 1.22 lambda by, you see A by f is 2 sin theta, is here 2 sin theta. A by f is here 2 sin theta, that is 1.22 by, that is this value will be there. We can divide it. Now here, if I want to further increase the resolving power, what we do, in order to increase the resolving power, we introduce a liquid between the object and the lens. We introduce a liquid. Now, the objective in this case, in which case if we have a liquid, if we have introduced liquid here, then the objective in this case is called oil immersion objective. The resolving power changes to R is equal to this n sin theta by 1.22 by 2 is nearly 0.61 lambda something. This quantity, so here you see n times the resolving power is increased. So the quantity here, n sin theta is called the numerical aperture of the lens. So in all the objective lenses, the manufacturer writes this quantity n sin theta as numerical aperture of the lens. So you see here, the resolving power R for oil immersion objective depends on something 0.16 lambda or something, this lambda. For optical microscopy, lambda is in the range of 4000 angstrom to 7000 angstrom. So if I want to increase the resolving power of my microscope, more this we require less to be lambda. Now when we use electron microscope, then the matter waves, the electron waves, matter waves has a smaller wavelength than our optical waves. As a result, the resolving power of electron microscope is more than optical microscope. So because lambda for electron waves is laser, lambda for electron waves is given by h by p, which we will study in modern physics. So now let us see what is Fresnel distance, which determines that whether we have to consider the diffraction effects or my result can be also predicted by ray optics. That is the validity of ray optics, the boundary. This Fresnel distance is going to decide the boundary between ray optics and the diffraction effects. So this is our slit. This slit has a width A. This is A, and on this screen somewhere, suppose this distance is D, then we get a maxima, this intensity distribution. This will be called our central maxima. So almost most of the energy is confined within the central maxima. There are some energy, little energies here, but maximum energy is confined. Suppose this is the angular position. Suppose I call this angle as theta. Then if this is a rectangular opening, then we know that it is sin theta is given by lambda by a, 2a. And if it is a circular opening, then it is 1.22 lambda by a. So the order of angle of this, theta is sin theta is lambda by a. So theta is lambda by 2a. So now if I consider this whole angle as theta, this angular width has the order of theta is equal to lambda by a. So this is the order of angular width. The order of the angular width of the central maxima is theta is equal to lambda by a. So this whole angle. Now this is my slit width A. So you see, if as a screen, if I take a screen and if I move this, then you see if I place a screen here, the central maxima has a width this. If I put a screen here, the central maxima has a width this. So as you go on, the width of central maxima will change. So if I assume my screen to be at this place where the width of the central maxima becomes equal to a. So this distance is called ZF. So we call this distance as ZF, Fresnel's distance as ZF. Now if my screen is closer than ZF, then you see this is an opening. If I have a parallel light here, then even if I neglect diffraction effect, I will get that this light is within this region. That means the validity of ray optics will be there. What is this width here? That width will be this phi into ZF. So if the distances are closer than ZF, if the distances are closer than ZF, the ray optics also gives the result, and beyond ZF distance, the diffraction effects dominates. So the results given by ray optics will not be accurate. So better results beyond ZF if we have to calculate, then the diffraction rules beyond ZF and the validity of ray optics is before ZF. Now if you want what is that ZF, so this width must become equal to this A. So what is the ZF? This width A, this is A will be equal to ZF times this angle, that is lambda by A. That is ZF is equal to A square by lambda. That means A square by lambda is where A is the diameter of this. If it is circular opening, if it is rectangular opening, then this is the width. So before ZF, if any distances are involved before ZF, then ray optics will also give the correct or result, and if my distances are beyond this ZF distance, then the result will be better given by diffraction phenomenon. So this is the validity of, so ZF, the Fresnel distance, determines the validity of ray optics and wave optics. Now let us see with one more diagram. Now you see this is my diffraction slit and this is the screen. placed at ZF distance. So suppose I assume that the light, we assume ray optics, and this is a plane wavefront. So that means these are the rays. So the ray optics tells that the rays are going to be confined within this distance. So without any diffraction, if my distances are less than ZF, you see ray optics tells that almost all the light will be within this region, and the diffraction patterns also tells that the central maxima is within this region. So most of the light is within region. So without the diffraction effects, if the distances involved are less than ZF, ray optics is also going to give the correct results. So this is the validity of ray optics, the boundary between ray optics and the wave optics.